Okay, so thank you for the introduction. It's a pleasure to be here and present the research we've been doing at Nethermind Research. So I will talk about folding. So let's start with some context. So let's take a relation R, and let's see what folding is about. So R consists of pairs, X, W. X is an instant, W is a witness. And a folding scheme is an interactive protocol between a prover and a verifier, where the prover has two instance witness pairs, X1, W1, X2, W2, and the verifier has the instances. All right? And then the prover and verifier interacts so as to create a new instance witness pair, X3, W3, with the following key property. If the new instance witness pair is in the relation, then the initial two instance witness pairs are in the relation, except with negligible probability. Okay? So basically, takeaway, folding in a nutshell, is folding is an interactive method that allows to reduce the task of proving two instance witness pairs to proving one instance witness pair. And yeah, so in all folding schemes, commitments are crucial. And actually, we only consider relations where the instance contains a commitment to the witness. So really here, when I write xi wi, I really mean that xi, the instance, has two parts, which is the real instance and then a commitment to the witness. Okay? So we always deal with this type of relations, and you can always, given any relation, transform it into this type of relation. So really, a folding scheme takes two instance witness pair where the witness is committed and gives you a new instance witness pair with a commitment to the witness. And usually, in most cases, the commitment has to be homomorphic, which means that the commitment to a sum of witnesses is the sum of the commitments. All right, so for those of you who have never seen a folding scheme, here is how it works if you look at it from 5,000 kilometers distance. So take two instance witness pairs that we want to fold. So as I said, the prover knows everything, knows the witnesses and the instances. The verifier only knows the instances. And now prover and verifier exchange messages for a while. Eventually, the verifier samples a random message, a random challenge alpha. And then the new instance witness pair is output, and it has the following form. The new instance is a linear combination of the initial two instances using the randomness alpha. And the new witness is a linear combination of the previous two witnesses. And yeah, okay, so, but the verifier has to obtain the commitment to the witness. And here is where the homomorphicity of the commitment comes into play. For the verifier to compute the commitment to the new witness, we use the property of homomorphicity. We use this formula in here, and this allows the verifier to compute this commitment, because the verifier knows these two commitments. So this is folding from 5,000 kilometers away. Almost all folding commitments work this way. And this is all you need to know for this talk, except in the end. In the end, it gets a bit more technical, but it's only in the end. Okay, so usually, the commitment scheme is a Pedersen or KZG scheme. For example, Nova, Hypernova, Protostar, Protogalaxy, and Along, etc. use Pedersen-based schemes. This scheme has some inconveniences. One is that you are required to live in a big field, so your witnesses have to live in big fields of at least 250 bits. And commitment can become really expensive, especially if the vector has large entries. If the vector has arbitrarily sized entries, these commitments are extremely expensive. And it's also a headache and conceptually very complicated, and also computationally complicated to recurse over. So it is hard at proving that, for example, a folding was done correctly, because you have to arithmetize for a foreign field in your field. You have to prove that some elliptic curve operations were performed correctly. And yeah, so this is kind of an engineering headache and a computational problem also. And also, something that happens if you are using commitments that are Pedersen or KZG scheme, the KZG PCS, is that you are then kind of bound to use a KZG-based NARC like the original Plonk. But how about folding and using Starks? So first of all, let's describe what I mean by Stark loosely. By Stark, I mean a SNARK that uses a code that is code-based, so uses some kind of code for its commitments, and then it commits to these codes with Merkle trees. And maybe it's easier to just give an example. So you can think of ETH Stark, which is, by ETH Stark, I mean the original Starkware Stark protocol, Plonky 2.3, Boojum, Read 0, etc. And a very good property of these schemes is that you can configure them on small fields. For example, Goldilocks, which has 64 bits, Baby Bear, 32, M31, which has 32. Maybe 31 bits, 32 bits, but roughly this number of bits. This is really good because, first, these primes have certain properties that allow to build smaller arithmetizations of computations. And second, computations overall are cheaper because field elements are never very large here. If you take the inverse of a field element, the inverse in Baby Bear, for example, will have 32 bits instead of 250 bits if you are working on a large field because you are bound to use elliptic curves. So that's very nice. But if we want to use the scheme, the folding scheme seen from 5,000 kilometers away, I described previously, we run into problems. The first problem is that Merkle trees are not homomorphic. And we cannot just change it for some homomorphic scheme that works on elliptic curves because there's no secure elliptic curves that use small fields. And also, depending on how you do folding on Starks, it might not be worth it. So now I will explore this last point, and I will come to the other points later. So let's see first let's see an anatomy of a Fry-based Stark, which is all of the examples I mentioned before. So a Fry-based Stark proceeds as follows. So first you compute the trace, or if you want the values, the wire values of the circuit. Then you encode the trace, which means that you take the trace columns, you interpolate them to create polynomials via an inverse FFT, and then you evaluate those polynomials on a larger domain via an FFT. This is called computing the low-degree extension of the trace. And then you commit to the low-degree extension with a Merkle tree commitment. And then there's some extra things that happen. You compute some quotients, commit to the quotients, and then apply Fry. So in a talk at SBC this summer, Eli Ben-Sasson gave a breakdown of this cost. The trace for Stu proving Blake hash computations. The trace generation cost 46% of the whole process. Computing the low-degree extension cost 28%. Merkle tree around 13%, and the rest 13%. Okay, and yeah, so here there's a remark. The Merkle tree uses the Blake hash in this case. If you are interested in using recursion or folding, and if you want to use folding, you are in a setting where you are probably interested in recursion if you cannot do folding, so it's a reasonable assumption. Then step 3 becomes more expensive because you probably don't want to have Blake in the whole Merkle tree. You probably want at least to use Poseidon in the first level. And so yeah, so this is one of the points I wanted to make, which is that even if Merkle trees were homomorphic, you don't want to fold here, right? Because you don't want to compute the trace, compute the low-degree extension to it, the Merkle tree, and then fold, right? Because what are you saving? You are saving 13% of the proof cost. So what we want to do is to commit to the trace. So we commit at the first step. And besides removing the cost of the second step, we are also reducing by a lot the cost of the Merkle tree commitment, because the Merkle tree you are committing to has a larger size than your original trace, because there's this blow-up factor that appears in the low-degree extension computation. So in the best case, Well, worst case for this saving is you save 50% of the cost. But if your rate is lower, then you save even more. And this is a difference that the approach I'm discussing today has with the protocol accumulation without homomorphism, where you are forced to fold at this step. You are forced to encode the trace for soundness reasons. You are forced to use the code properties. You are just forced to use Reed-Solomon code properties. Okay, so let's recap what we want to do. We want to commit to the trace, not the low-degree extension. We want the scheme, the folding scheme, to be compatible with Starks. And this means that we want to work over small fields. We want the folded instance to be efficiently provable with a Stark. And since we are working with Starks, we want our instances to be heirs or Plonkish instances. And I'll come back to this CCS later. Okay, so here's a framework. Take R to be the heir or the Plonkish relation, and take two instance witness pairs in this relation. So the framework abstractly is as follows. The prover commits to the trace, which is the witness in this case, with a homomorphic commitment scheme. We'll talk about which later. Then we fold somehow in a way that the folded instance belongs to R or some similar, some relaxed version of R. So this is the folded instance witness pair. And then say we want to prove a folded instance. Then we would proceed as follows. The prover would compute the low-degree extension of W3, the folded witness, and it would commit to it as usual in a Stark-based proof. It computes the low-degree extension and commits to it with a Merkle tree. And then you prove that the commitment to W3, that's in the folded instance, and this Merkle tree commitment come from the same witness. And then you finish the proof that X3W3 is in the relation with a Stark. You just do the Frey quotienting and the whole Frey thing. So this is the framework, speaking abstractly. And now how do we instantiate it? So as we saw, we needed a commitment scheme that is homomorphic and that it is compatible with a Stark field, because when proving the folded instance, we want to use Plonky2, say. So the candidate commitment here is the ITI commitment, following the lead of the lattice fold paper by Bonnet and Chen. And then we need a folding scheme that folds pairs of heir or Plonkish instances into roughly heir or Plonkish instances. To deal with this, we look at heirs as CCSs, and we restrict to degree 2, which is a reasonable restriction. I think that the Cairo VM uses degree 2 or 3 heirs. And yeah, then if you are in degree 2, then heir or Plonkish is roughly a relaxed R1CS. It's not exactly a relaxed R1CS, it's a relaxed R1CS with more summons. And there's the Nova scheme that folds relaxed R1CS into relaxed R1CS. So we choose this one. This way, when we are done folding, we have something that's similar to an heir. The problem here is that there's no Nova type scheme that works over lattices. So our work, the work I'm presenting today is concerns this, is a design of this scheme. The scheme that doesn't exist. Well, didn't exist. Okay, so now crash course on lattices. So now it exists, it didn't exist before. Okay, so a cyclotomic ring has this form. If you know what a field extension is, a cyclotomic ring is an extension of a field, but you don't use an irreducible polynomial, you use any polynomial. So you take the ring of polynomials over with coefficients on a field, and you quotient it by the ideal generated by a polynomial. This is the set of all polynomials of some degree. And if fx is irreducible, then this is just a field extension. Otherwise, this ring is a direct product of field extensions. So a cyclotomic ring, you can think of it as a direct product of field extensions. And we show that it is possible to properly configure R, whatever this means, so that FQ is a Stark prime field. We have Goldilocks baby bear and the big Stark prime from years ago. M31 is work in progress, but I'm pretty sure we will deal with it. And the itai commitment scheme works as follows. So the parameters is just a matrix, which is sampled uniformly at random. Here we want to commit to vectors of length m, and k is just a parameter that we can choose. You can think of this kappa as being 5, for example. So it's like 5 times the length of the vectors. The input is the vector we want to commit to, so a vector of length m of ring elements. And the output is a commitment to, the output is the commitment, which is the matrix multiplied by this vector. And so the result is a vector of kappa elements. So think of 5 elements. So before I go into technical details, some words about the efficiency of this commitment scheme. So let's say that FQ is the Goldilocks field, and we configure R so that R is the direct product of 8 field extension of the Goldilocks field of degree 3. And we configure it like this because we need to guarantee that there's 128 bits of security from the module SIS assumption. An important observation is that then a vector of size 2 to the n can potentially be used to store 8 times 2 to the n trace cells, because the ring is this direct product, and direct products have additions and multiplications that are component-wise, so they are very easy to control. So you can take your trace and put cell elements in each entry here. So if we commit to committing to a vector to 2 to the n is, in some sense, like committing to 2 to the n plus the 3 trace cells. And we have these benchmarks that we run. So itai commitment for a vector of size 2 to the 16, which would be 2 to the 19 if we exploit this decomposition, costs 65 milliseconds. Merkle tree for a vector of size 2 to the 16 costs 14 milliseconds, but here we can only commit to 2 to the 16 trace cells. So if we compare it to committing to 2 to the 19 trace cells with Merkle tree with Blake, we get 50 milliseconds, so we get comparable speeds between itai commitments and Merkle trees with Blake for the same number of trace cells. And Blake is the fastest, or one of the fastest hash functions you can choose for Merkle tree commitment. If you have algebraic hashes, which you might need to do if you are doing recursion, then you are, the times are much worse. Already in 2 to the 16, you have 2.5 seconds commitment cost with a Poseidon Merkle tree. Okay. This is just a recap of itai commitment. So a huge caveat of itai commitment is that it is only binding when the vector you are committing to has small norm. And norm is the largest coefficient of an entry of the vector if you look at the entry as a polynomial. So this introduces several headaches when you want to fold. One is that recall that the folded witness is a linear combination of the initial witnesses. So there's 2 issues here. One is that even if W1 and W2 have small norm, W3 might have large norm, right? Because you take the linear combination, norm might grow. And then the commitment to W3 might not be binding. And there's another issue that is, even if 1 doesn't happen, in your relations, you want to have that the witnesses have bounded norm because you want to make sure that the prover is using a binding commitment. So after you do folding and you want to prove knowledge soundness, you should prove that the extractor gets W1 and W2 with small norm, and this is tricky to do. And lattice fold is a scheme that, okay, so lattice fold is a scheme that builds a lattice-based version of Hypernova that deals with these two issues. So lattice fold works, it's like Hypernova, but it has extensions to deal with these two problems. Okay, so the way lattice fold approaches one is the following. So first, the CCSs are linearized, as in Hypernova, with a sum check. Okay. If you don't know what a CCS is, here you can just replace CCS by relaxed R1CS. Hopefully you know what relaxed R1CS is. And then what lattice fold does is the witnesses are decomposed into, say, base 2. So each WI is decomposed into WIJs, and the WIJs have tiny norm. And then they show that each WIJ is a witness to a linearized CCS instance. So now you have 2K linearized CCSs, but each witness has tiny norm. And now in lattice fold, they fold these 2K linearized CCSs together. And you don't have this problem because you are guaranteed, well, you know that the WIJs have tiny norm, and you choose parameters and challenges in a way that you are guaranteed that if the prover is honest, then when you fold these 2K instances, these 2K witnesses, the result has sufficiently small norm. So that's how lattice fold approaches one. This is just a recap of the last slide. And our approach to one is the following. So we want to do Nova-style folding. We don't want to linearize, because if we linearize, we get out of error or Plonky's constraints. And also, we don't want to use sum check, because sum check has several issues. One, it can be very expensive unless you optimize it heavily. And second, it is hard. It introduces overhead for when you want to do IBC. So what we do is we decompose WI as in lattice fold. And again, we can show that the new WIJs are witnesses for relaxed R1CS relations. But the problem here is that we cannot control what happens with the error terms, with the norms of the error terms. And we cannot commit to those because we don't know that. We cannot guarantee that their norms will be bounded, will have small norm. So what we've realized is that in Nova, you don't really need to commit to the error term, because the error term is kind of implied by the witness, by the rest of the witness. So yeah, we realized this while dealing with this problem. And in this summer, we put a paper called Mova, where we just explained this trick, but on a normal setting with elliptic curves, which is called Mova. Later on, we realized that Mova is kind of a particular case of a variation of protogalaxy. So here we could also say we follow a variation of protogalaxy. And yeah, so obstacle 2. Yeah, obstacle 2, I will not explain it because of time constraints, but we do not, in lattice fold, they also approach obstacle 2 with a sum check. We don't use sum check, we use some other tricks. So we end up with a scheme that doesn't have sum check and has a constant number of rounds. Thanks.
Thank you, Albert. We have a couple minutes for questions, so if anyone has anything.
Thanks for the presentation. In terms of performance, how do you compare against normal free recursion?
We haven't checked.
Because even like the conversion from R and Plonkish to CCS, it's quite expensive as far as I know.
Well, you can always use some, you don't really need to turn it into a CCS necessarily. You can also work with R directly and introduce no overhead in conversion.
Thanks.
No more questions?
Yeah, small questions. Very open question. So, what would be? So you mentioned that one difference with the another work by Bunz and I forgot the second co-author.
Chen.
Yeah, exactly. Was that you guys are? So the difference was that your folding happens before the Merkle tree phase,
Yeah.
the fourth phase that you. Is there anything else that you would like to highlight? Are these works similar?
No, they are completely different works. So conceptually, the techniques used, they have nothing to do with each other. And in terms of performance, the difference is the one I explained.
Okay, but it's only a performance remark.
That was only a performance remark, yeah.
Okay.
Yeah, conceptually, they have nothing to do.
Okay.
All right, I think that's all. Thanks again, Albert.